Hello there and welcome back to this video series on control systems. Over the past few videos, we have been looking at approximating the experimental data to form asymptotic plot and also finding the transfer function from body asymptotic magnitude plot. However, in those videos, we have seen how to form the total body asymptotic plot by first tabulating the values, that is contributions of each term, and then summing them up. We will see a slightly different thing, that is how to sum them up in a graphical representation. So such approach is very useful for students who are graphically oriented. It will save them a little time in computing from the slopes of each of the terms. However, before going into such effort, it would be very helpful if you watch videos 55, 56, 57, and 58 to make the most out of this video. So after watching this video, a student will be able to draw the body asymptotic magnitude plot without tabulating the values and finding the total contribution. We'll try to do that on the graph sheet itself. We'll try to see how we do that with the help of an example as shown here. This is the open loop transfer function. This open loop transfer function has 1, 2, 3, 4, and 5 terms. Carefully note that we have expressed these terms in the time constant form. Okay, even if they are in the form of s plus something, you need to bring it into this time constant form. That is, all the forms will be of the 1 plus tau s form. Tau here is 1 over 2, tau here is 1 over 5, tau here is 1 over 10. So this term has a corner frequency 1 by tau, that is 1 over 1 by 2, 2 radians per second. This will have a corner frequency of 1 over 1 by 5, that is 5 radians per second. This term will have a corner frequency of 10 radians per second. We'll try to show all these on the semi-log graph sheet with the axis neatly laid down to show all the frequencies. Let us do that. Okay, so I've indicated the terms here. Okay, so on the graph sheet, in some corner, neatly indicate term 1, term 2, term 3, term 4, and term 5. This legend will gradually build it up as we are drawing the body plot. Okay, we'll try to draw body plot term by term. Okay, so we'll first consider the term 4, that is the constant term 4. Okay, this term is independent of the frequency radians per second. So at all radians per second, it contributes a decibel of 20 log to the base 10 4. That will come out to be approximately 12. So contribution of this 4 at all frequencies is 12 decibels throughout. Let us show that. At 12 it is constant throughout. I have indicated that here with letter C, that C is 0 decibels per decade, and we are drawing for term 1. Then the next term is of the form 1 plus tau s in the numerator. The corner frequency is 2 radians per second. So the contribution of this term 2 is 0 decibels all the way up to 2 radians per second, and then it goes up. Then it goes up because the term is in the numerator. It goes up with a slope of 20 decibels per decade. At the end of each decade, its value increases by 20. So it is 0 up to 2 radians per second and is going up. You can see at 2 radians per second, its value is 0. At the end of the decade that begins at 2 ends at 20, 2 times 10. So at 2 it is 0, and at 20 it is 20 decibels. And if you see at 40 it will be another 20 more decibels. So this term D is plus 20 decibels per decade, and it is term 2. Okay. The next term is the lone S term, the integrator S term in the denominator. It will be a line all going at minus 20 decibels per decade all the way down. Okay, let us show that. You need to be careful how you obtain this 20 decibels here at the beginning. It starts at 20 decibels and goes down with a negative slope, minus 20 decibels per decade. Okay, that is for term 2. B is the slope, which is minus 20 decibels per decade. Okay, you need to be very careful as to how you obtain this 20. If you just write it down, you will very clearly see. The next term is a first order term with a corner frequency of 1 over 1 over 5, that is 5 radians per second. Up to 5 radians per second, the contribution of term 4 is 0, and from there it will fall down at minus 20 decibels per decade. Let us show that. In 5 it is 0, and then it is going down. We have written B. B is minus 20 decibels per decade, and this is term 4. We need to nicely label each term, otherwise we'll get confused, and the resulting BAMP, body asymptotic magnitude plot, may be wrong. The term 5 has a corner frequency of 1 over 1 over 10, that is 10 radians per second. Up to 10 radians per second it is 0, and from there it will fall down. It will fall down because this term 5 is in the denominator. Let us see that. And we nicely labeled it. B is minus 20 decibels per decade. You have seen, instead of writing minus 20 decibels here, minus 20 decibels per decade here, minus 20 decibels per decade here, we have labeled it as B, and we simply indicate B, colon term 5. So it indicates that this graph is coming out of term 5, and the slope here is minus 20 decibels per decade. Once you have drawn all these, you can sum them up graphically. Okay, but you need to note, because I have so many colors in PowerPoint, I have drawn them in color, so many colors. But in your examination, you have to draw all these curves for term 1, 2, 3, 4, 5 very light, using perhaps a H pencil. Draw them so that they are visible but not prominently visible. What should be prominently visible is the total body asymptotic magnitude plot. That is why you will draw the net result of all these in dark line, perhaps using HB pencil. So here is what we will do. At 0.1 radians per second, if you go up along this 0.1 radians per second, you see that two terms contribute, 12 and 20. All the other terms do not contribute anything at all, because it is 0 all the way up to 2 radians per second. Other term is 0 all the way up to 5 radians per second and 10 radians per second. So if you see, sum the contribution of each of these terms, there is 0 from term 2, term 4, term 5, and then term 1 contributes 12 dB, and term 3 contributes 20 dB. So 20 plus 12, 30, 2. Let us show that. Okay, we did that. And next, the frequency of importance is 1 radians per second. At 1 radians per second, the contribution of term 1 is 12, because this 12 is constant all through. Term 1 is 12. Term 2, it is 0, because its term 2 is of the form 1 plus tau s, and it is 0 all the way up to 2 radians per second, and all the other terms also do the same. Term 3 is also passing through the 0 dB line. So if you sum up all the contributions of terms, you will be left with this 12, because only term 1 has a contribution. All the other terms do not contribute anything at 1 radian per second. If you come to 2, 2 also, all the terms contribute 0 except this term 1 and 3. This term 1 is 12, term 2 is a little negative value. And if you sum both of them up, that is, read what is the value here, and then 12, 12 minus this is 6. Similarly, you do it at 5 radians per second. There is a negative value. What is the value here? You read it. What is the value here? You read from the graph, and this is 12. If you sum them up, you will see that it forms a horizontal line here. The C indicates, you can see 0 decibels per decade. And similarly, at 10, you do it, and then at 20, you sum up whatever is the value here plus the value here plus the value here. Of course, taking sign. The value here is negative, the value here is negative, the value here is negative. This is 12, and whatever is the value here is positive. If you sum all of them up, it comes down to minus 12. Similarly, at 50, if you go vertically up, you can see this value is negative, this value is negative, this value is negative, this is positive, this is positive. If you sum all of them up, you get another term. So you can join all of them with a smooth, with straight lines. This pink line is formed out of straight line segments. Okay. Again, remember that the pink line is the dark one. You will draw with HB pencil, and all the others very light. They are visible but not prominently visible, drawn with H pencil. This pink line is with HB pencil. Okay. Just for illustration, I'll try to remove all these and draw the exact curve on the top of it. You don't have to do that. You leave all these lines as it is in your examination. Just for illustration, now I'm trying to erase all those. Okay, all these terms, they disappear slowly one after the other, and you're left with this ABC. Okay, we'll show the exact plot on this just to give us a little bit of confidence that this BAMP, body asymptotic magnitude plot, is really useful. Okay, so what I'll do is I'll do all the computations I've already done, that is substitute S is equal to j omega, form f of j omega, and at each value find out what is the magnitude, take logarithm, multiply by 20, and do all that and compute exact value. The exact one is shown in green here. You can see that the approximation is very close. You have a maximum error of, for example, 3 dB here, and slightly lesser dB here, and even lesser dB here. So the approximation is very good. So to sum it up, we have seen procedure for drawing BAMP, that is body asymptotic magnitude plot. without actually tabulating the values. We inferred them from the graph sheet. Okay, obviously this gives the same BAMP as the earlier attempt, but this is easy for students who are more graphically oriented. I think that's all we have for now. Have a great day.